Hi, this is AP Chemistry topic 7.12. Common ion effect. Today's objective is to be able to identify the solubility of a salt and or the value of the KSP for the salt based on the concentration of a common ion already present in solution. So these types of ion problems we're going to look at, we're actually going to apply Le Chatelier's principle to a KSP type of problem. We have a slightly soluble solid and it's added to a solution, and it contains some of the ions that are going to be like that you can find in the solid itself. So you'll see in a bit. So we have zinc hydroxide, which has some precipitate present. When you have a KSP type of problem, it's best for you to, where is it at? Where am I looking for? There I am. It's always best to start off by writing out your dissociation equation. You start off with a solid producing the ions, but you have the double-sided arrow and the KSP expression too. So these types of things should be fairly easy to do. So let's say the KSP for this is 3.0 times 10 to the negative 17. So you have zinc hydroxide, and it is dissociating into zinc 2 plus and 2 hydroxide ions when it's in solution. According to Le Chatelier's principle, we know that if we are going to add more zinc to, if we add zinc to nitrate or sodium hydroxide, so notice how we have zinc here and OH in the sodium hydroxide. By adding those, you're going to add it to the product side, which according to Le Chatelier's principle, by adding those products, you're actually going to shift the reaction to the left, making more reactants. So what you're going to see is technically more precipitate forming according to this. So looking at this quantitatively as opposed to qualitatively, we can use an ICE chart or ICE table to organize this information. So the question is, how do we calculate the molar solubility of zinc hydroxide in a solution of 0.10 molar NaOH? So notice that both solutions actually have the hydroxide ion. So that's why it's called a common ion problem, because they have some ion in common. Nice, right? So looking at this, we have our ICE chart kind of set up already for us. So luckily, the zinc hydroxide, because these are going to be salts, so it's added to solution. So the salt will be solid, so we can ignore it completely, but you have to make sure that when you dissociate it, that it is actually the correct, it's in the correct ratio. So zinc 2 plus and then 2 OH hydroxide ions. So my initial, we're going to assume that since it says there's nothing dissolved yet, we're going to assume that the zinc 2 plus is 0. And then we have actually the concentration for the hydroxide ions from the NaOH. So it says that NaOH, that when it dissolves, it's Na plus aqueous and then hydroxide aqueous. So you have a solution of NaOH added to water. So because it does not give us the KSP, that means that we assume that it is completely soluble. So because of this, any molarity for the NaOH, or it kind of translates to the sodium and hydroxide ions here. And because this is completely soluble, we can assume that this OH, and when it's mixed with the zinc hydroxide, it's going to be the same concentration there, so 0.10 molar. So what does that mean? Well, we have to think about how much these things change by now. So luckily, we look at the zinc 2 plus, and it changes. We're going to assume that it changes by x. From there, we can assume that the 2 hydroxide ions will change by plus 2x. So at equilibrium, we have x for zinc 2 plus and 0.10 plus 2x for the hydroxide ions. Then what you need to do is be mindful that what you're doing is you're solving for the value of x. What is the molar solubility? That's what you're solving for. What is x? And because the KSP we saw briefly earlier, 3.0 times 10 to the negative 17 is really small, luckily we can assume that the X in the hydroxide ions are going to be negligible. And because it's so small, you can assume that it's not going to really impact it too much. But do not do that with the X from the zinc 2 plus. You still need that. So you can solve it by using your calculator, or you can actually assume as well. And luckily, because of the small KSP, the assumption is good. You see that when you solve it with your graphing calculator with the solver function, you end up with 3.0 times 10 to the negative 15 molar. And that is the molar solubility because that's what X is equal to. And if you do the assumption way, in case you kind of need to, because maybe you don't have a graphing calculator or the one with the solver function, you can assume that X is negligible, so you don't worry about it, and you just kind of solve for the rest. And you should still end up with 3.0 times 10 to the negative 15. So just I kind of skip this part, but make sure that when you set up your KSP, you're doing it correctly. So KSP equals zinc 2 plus times hydroxide squared equals 3.0 times 10 to the negative 17. You see that when you're using your ice chart, the X is zinc 2 plus, and then you're just kind of substituting with what you have at equilibrium. And you're going to solve for X. So typically what we're going to see that the common ion that is added is going to include maybe sodium, maybe nitrate, ammonium, and potassium, all those SNAP ions we talked about way back when. Feels like forever ago, by the way. Anyway. So write a balanced equation for the dissolution of calcium hydroxide in pure water. Calculate the molar solubility of calcium hydroxide when it's dissolved in 0.2 molar calcium nitrate solution. The KSP of calcium hydroxide is 1.3 times 10 to the negative 6. So first thing we would need to do is know and recognize the solution of calcium hydroxide. You have CaOH2, it's solid, it's dissolving. You have calcium 2 plus ions and then 2 hydroxide ions. Okay, very good. So calculate the molar solubility. You're actually given a calcium nitrate solution. So you see that nitrate that we talked about with the SNAP ions, that's going to be in the solution. So based on the balanced equation we have, my KSP will equal calcium 2 plus times hydroxide ion squared. And according to the problem, we have 1.3 times 10 to the negative 6 equals calcium ions times hydroxide ions squared. So we're going to complete an ice table and in order to figure out what is the molar solubility in the end. So we have ice. So calcium hydroxide is negligible according to this because it's all solid, so it doesn't matter. So we have Ca2 plus and O2OH1 minus. So pay attention to what it's dissolved in because that will tell you what is the concentration. So you have calcium nitrate. So it's dissolved 0.2 molar. So this means that this is going to dissociate completely. So you have calcium ions and nitrate ions, 2 of those. Oops. So because calcium is 1 mole according to our reaction, we can assume that it's just going to be 0.20 molar. And because there's nothing else dissolved in there, we can assume that there's no dissolving of the calcium hydroxide just yet. So we can actually assume that the hydroxide ions are 0. So that's what we're going to start off with. So the change. How does it change by? So according to our coefficients, calcium would increase by just 1x. So it's 0.20 plus x. hydroxide ions would increase by 2x, so 0 plus 2x is 2x. So what you do now is need to solve for x. So 1.3 times 10 to the negative 6 equals 0.20 plus x times 2x squared. So I'm going to use my calculator, but you can also assume that since it's a small KSP, x is negligible, so the 0.20 plus x ends up becoming just 0.20. If you have your graphic calculator, you can actually skip, a bunch of steps to solve, etc., and just kind of go from there. So maybe a good idea to get the TI-84, the solver function, or if you don't need to, luckily the problems on the test should have KSPs that are small, or the constants that are small, so you can the values are going to be small, so that you can assume that the x is negligible. But I'll just say that x does equal 0.0013 molar. But if you don't have the graphing calculator, 1.3 times 10 to the negative 6 equals 0.20 times 4x squared. 1.3 times 10 to the negative 6 equals 0.80x squared. Then divide by 0.8 on both sides. 1.6 times 10 to the negative 6 equals x squared. Square root of both sides, you'll end up with 0.0013 molar. So that means that my molar solubility is that value. What would the molar solubility be of silver chloride AgCl if the solution is also 0.00100 molar for sodium chloride? The KSP for silver chloride is 1.80 times 10 to the negative 10. So you should be happy when you see a KSP value that's less than, it's really, really small. That means your X is going to be negligible, but you still need to go through the process. So sodium chloride is completely soluble. So any molarity that you have for sodium chloride, it will transfer over to the chloride ion. So just really quick, you have sodium chloride S, solid, produces Na+, and then Cl1 minus. There's no KSP, so we're going to assume that it is completely soluble. So that we know that our chloride ion concentration is going to be 0.00100 molar. So we have our silver chloride. Just write out the equation. So some things to be mindful of. We're unsure of what we're starting off with for the AgCl. So in the end, that's going to be like my X. So it's funny. Anyway, so then silver ions and chloride ions, because of they're all 1 to 1 to 1, the concentration for the AgCl, or the molar solubility, I'm sorry, it's going to be X, 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 and all that. It's going to be what we're going to be solving for in a second. So in terms of our ice chart, though, the initial, because we don't really have anything for silver in terms of anything being dissolved initially, it's going to be 0. And because you have silver chloride mixed with the sodium chloride, we can assume that because of the common ion effect, that the concentration for chloride in AgCl would be the same as the chloride from the sodium chloride, so 0.00100. These will change, are going to be produced, so it's plus x, because both of these do not have any coefficients, so x 0.00100 plus x. Sounds like I'm speaking in binary. Anyway, KSP equals silver ions plus chloride ions. 1.80 times 10 to the negative 10 equals my concentration of X, or silver times my concentration of my chloride ions. We can assume that since X is small, the KSP since X is small because the KSP is small. So I just plug this in my calculator. I got X equals 1.80 times 10 to the negative 7 molar. Since X is the silver ion concentration, it is also the molar solubility for AgCl. So kind of like it's 0.00100 molar for sodium chloride. When it's put into solution, it's going to ionize into 0.00100 molar for sodium, and for the chloride ion, same thing here. With this addition of the concentration of sodium chloride, the molar solubility for silver is now going to be 1.80 times 10 to the negative 7 because it's the same for the silver chloride. That's going to be the molar solubility for silver chloride. So just to kind of write it out, so since X is Ag plus, it is also the molar solubility for AgCl. All right, if you have any questions, please let me know. Thanks.